Hi and hello everyone. In the previous lecture we have seen the definition of Markov chain and some examples and certain few properties, but not really properties that with respect to that something like a multi-step how you can compute and everything. Okay. Now what we will do in this lecture is we will look at little bit more properties of Markov chains. And the first thing that we will talk about is what we call is accessibility. Okay. It's pretty much clear what we mean by that. Its state J is said to be accessible. It's accessible from I if there exists an n such that this is strictly greater than 0. Okay. That's what we mean. It means R state J can be reached from state I if there is a step, right, at which you can reach the multi-step. In terms of this multi-step transition probabilities, we are defining it. Okay. If J is not accessible from I, then probability that you will ever be in J starting from I is obviously would be equal to 0. See, more of these properties that we are going to see, you will see that you can prove analytically, but it's intuitively in a probabilistic way. If you think then things will be clear. You don't need to worry too much get into the proofs or anything, because it should be true in an intuitive way. That's how you will see it. That's what we call it as a probabilistic reasoning would be sufficient enough to understand the properties and why and how that should be true. So it is more of this. So accessibility, which means that you are starting at some state I, say for example, you are starting at some state I and you will reach state J if there is a way to reach, maybe going through different states. Ultimately it may not be possible in one step, maybe it is possible in 2 steps, maybe it is possible in 3 steps and so on. There is some step at which it is possible, right. Then you would see that it is J is accessible from I, or we will say that J can be reached from I if this is true. Okay. Now communication means it is also the reverse way is also if it is accessible. Simply saying state J is accessible from I and state I is accessible from J, then we say both I and J communicate with each other, right. So it is I and J communicate if I and J are accessible from each other, which means there exists some n and some m such that these probabilities are strictly positive. The n step and m step probabilities are strictly positive. Now the notation wise, like in the typical way, we will use this when J is accessible from I, and it will be in this form when I and J are communicating. The double arrow would indicate communication and the single arrow, one directed arrow will be accessibility. Okay. And this communication is an equivalence relation, meaning it satisfies what we call reflexivity, symmetry and transitivity. What is reflexivity? It is I communicates with itself, I communicates with J, then J communicates with I, symmetry. Transitivity, if I communicates with K and K communicates with J, then I also communicates with J. Okay. This relation, this communication relations partition the state space into equivalent classes, and that will be called as communicating classes. So, will be called communicating classes. So, the whole state space S now will be broken into classes of where each of these is a communicating states would be there in any particular class, like. So, that's what it is. So, this basically partitions mean it divides the state space into equivalence classes. Okay. And if all states communicate with each other, which means there is only one equivalence class, if all states communicate with each other, then the Markov chain is said to be irreducible. That is, if there is a single communicating class. If not, if there is more than one communicating classes are there, then that means the chain is reducible otherwise. Most of the time, we will be dealing with this irreducible Markov chain, but of course, the theory is also required for how to handle if chain is reducible, okay, right. So, this is what are the properties of accessibility, communication and irreducible or reducible. Then we have the notion of what we call a closed set. So, we have a state space S and we have a subset A state space S and a subset A, and this A is said to be a closed set if no one step transition is possible from any state in A to any state outside A, right. If that is the case, then this is called a closed set, which means that from once you reach into that set, then you do not have a way of going outside of it in a way, right. That is what it is, you call closed sets. Absorbing state, we have seen it earlier case, we just mentioned it, but this is what is precisely it means. If a closed set contains only a single state, right. So, when it is basically a, which means that the communicating classes or whatever you have, if it contains a single state, then the state is called as an absorbing state. So, a state I is absorbing in this particular DTMC case if this is true, right. We have seen in that example, one of this example that this is situation was true, that Pii for some I, if it is equal to 1, that means it is there in currently in I and it will be there in I in the next step as well, and forever it will be. So, that is so the process got absorbed into the state, that is what is the terminology that would be used in this particular case, right. Now, if S is closed and does not contain any proper subset which is closed, then we have an irreducible Markov chain, right. If S contains proper subsets that are closed, then the chain is reducible. So, you can also talk irreducible and reducible in this manner as well. Okay. You can see like if there is a single communicating class and that is a closed class and it does not contain any proper subset which is closed, right, because all of them forms a single class, then we have an irreducible Markov chain. Suppose if it is not the case, then you have subsets which are closed more than one, okay, then the chain becomes a reducible chain. So, if a closed subset of a reducible Markov chain contains no closed subsets of itself, okay, then it is referred to as an irreducible sub Markov chain, because then that particular sub Markov chain will have its transition probabilities will behave as if that is itself is a Markov chain, because that P would itself be a stochastic matrix. So, one can handle that chain separately as a independent of all other states, that particular class alone you can treat as if it is an irreducible Markov chain and you can handle that. That is the reason why you look at that way. Now, let us look at here, for example, the first example we will see. So, what we have here, so suppose the states are say 1, 2, 3, 1, 2, 3. Okay. Now, what you are seeing here is that whether what is the situation here if you look at it, how many classes are there and so on. So, now suppose if I call this, as we know already about this quantities, right, 1, 2, 3. So, 1 to 1 it is half, I mean with this help of this it is easy to write it down. This 2 to 1 it is half, 2 to 2 it is 1 by 4, 2 to 3 it is 1 by 4, 3 to 2 it is 1 by 3 and 3 to 3 is 2 by 3. Now, whether 2 is accessible from 1? Yes, right, from 1 you can access 2. Whether 2 is accessible from 3? Yes. Whether 1 is accessible from 2? Yes. Whether 3 is accessible from 2 or 2 is accessible from 3, everything will be there. Now, whether I is this 1 is accessible from 2 even in one step, right, or first time self loop, then here. So, in 2 step, it can be 2 is accessible from 1 in 1 step, in 2 step, but we need at least one number, right, at least in 1 step it should be able to reach. So, that is basically that you are having it here, right. So, this whole thing, the state space of this forms a single communicating class of 1, 2, which is a closed set here, right, which is a closed set here, and there is a single communicating class 1, 2, 3 for this, right, and there is no absorbing state, it is a single closed set, single communicating class, all the states are communicating with each other, all the states are accessible from each other, right. That is what you have it here. About this example, we will see little later. Now, we will define, after this properties of state, now we will define hitting time. What do we mean by that? It is, you pick any subset of A and you are looking at the hitting time, which we call Ta, is defined to be infimum or minimum of n such that xn is in A. Okay. So, with the convention that if this is it is never, if this set is empty set, then this is infinity, because you are never going to be reaching there. So, it is basically what you have this state space and you have a subset of state space, right. Now, you are trying to see hitting time means the time you will reach to a state inside the set A for the first time, that is minimum time at which your xn will be inside this A. That is what you call it as hitting time of this set A. So, this is the first time after 0 when the chain enters A, right. If Ta, so and hence because if this is also called this the first passage time or first return time to A, right. Now, this particular thing, if it is a single state, we might simply denote it as a T suffix I without this set notation of this I, right. So, this will be just a notation. First passage time or first return time plays a crucial role in the analysis of different Markov models. So, what does that mean is that it is basically first time something is reached a particular. Suppose you are looking at building wealth and then you are starting at some 100 and you are looking at when you will reach 1000, then you will say that for the first time 1000 is reached, when, what is the timeline, when it is needed, right. So, that is what would represent in this particular case, okay, right. Then based upon this quantity, this hitting time, we can also classify the states into differently, and these are all the basic definitions of that. Now, a particular state I you call is a recurrent, sometimes the word persistent used, but recurrent is what we will be following it, is recurrent if this probability is equal to 1. What is that probability? Starting from state I at time 0, starting from I at time 0, the probability that the reaching back to I for the first time, okay, after that time 0 is finite. So, in a finite amount of time, you will reach back or you will return back or you will come back to I after starting from state 0, so state I at time 0, in a finite amount of time you are going to come back to that particular state I, and that is what you call it as recurrent state or persistent state, okay. And probability of this is equal to 1, that is what you mean. That means, if I say the state I is recurrent if and only if this probability, this notation Fii, small f suffix ii is basically meaning this, which means starting from I, x0 equal to I and xn equal to I for some n greater than or equal to 1, right. If for some n, it could be n is equal to 1, 2, 3 and so on. So, that is what this event is. Starting from this event, probability of this particular event, probability of given x naught equal to I, xn equal to I for some n greater than or equal to 1. If this probability is equal to 1, that is what you call it FII. Okay. And a state I is called transient if this probability is strictly less than 1, which means you may come back, but there is a possibility that this is not equal to 0. So, that means that you may be finite, but after some time there is a possibility that you may not return back. So, it may not be possible to return back to in the finite amount. So, there is a possibility at least that you will not return back to the state I once you started out of state I, right. So, that is what then you call it as the transient state. So, recurrent, transient. So, the state could be either transient or recurrent depending upon whether this FII equal to 1 or FII is less than 1, right. And recurrent can further be divided into two types of recurrent depending upon this is you are sure to return back to I in a finite amount of time, but what is the expected time to return? That is what it denoted. If the expected time to return is null, if it is infinity, then you call that as null recurrent, and if the expected time to return to that state, if it is finite, then you call that as a positive recurrent. Okay. Remember, it could be a probability, it could be a distribution, it could be but the expected value need not be finite for every distribution, right. So, that is what it would amount to here. So, now let us be more precise on this. So, we can define this quantity FII in the superscript bracket n, meaning that the chain starting in state I returns for the first time to I in n transitions, in exactly n transitions. It starts at I, comes back to I in exactly n transition. The probability of that is what you call it as FIIN. This is different from PIIN in the superscript, right, n. That is meaning that you are coming back to I in n steps. That may be first time, that may be second time, that may be third time, and so on. But here this is you are talking about the first passage or first return. This is basically first return because you are starting at I, you are coming back to I for the first time in n step. What is the probability of that? That is what it is. Okay. Now, here if you look at FII, we defined xn equal to I for some n greater than or equal to n. Now, if you separate this for each n, that is what this notation would be. Now, if I sum all those events, then what I am going to get is FII, right. So, this FII, which means that you will come back to I for some n, right, is basically union of those events. When you take probability, this becomes sum. So, that is what you are getting it here, right. So, this FII is nothing but this particular sum. Now, for a recurrent state, since this is going to be equal to 1, so you have certain non-negative numbers which sum to 1. So, they describe a probability distribution, right. So, that means this quantities, this family FIIN for n greater than or equal to 1 defines what we call as first return time or recurrent time distribution, because it is distribution because the probability is sum to 1, right, for a recurrent state. Remember, this is for a recurrent state. And the mean recurrence time, which we denote it by MII, capital MII, which is what this quantity is essentially then will be given by this quantity if in terms of your FIINs, it is the distribution. Okay. Now, this recurrent state is positive recurrent. If I want to say in this manner, positive recurrent, null recurrent, instead of this expected value in terms of this MII, if my MII is finite, and null recurrent if MII. So, there is a typo here, it is MII is infinity. So, then is positive recurrent. Similar to this, one can also talk about first passage time. So, here Fi starting from I, you are looking at the quantities which you are coming back to I. Now, this starting from I, if you are looking at some state j which is not equal to I, then exact same thing we will be talking about that Fij of n would be the probability that state starting in I reaches state j in n steps for the first time, right. Then its properties and its distribution whenever that is equal to 1 and so on. If it can be done, if it can be reached, then always this will be 1 and its distribution will be first passage time distribution. It will be similar to this, that is what you might see. Another concept which is also relevant, this is mainly in the discrete time. Of course, continuous time you do not have this notion of this periodicity, but in discrete time you have this. What is this? You look at Pii n step probabilities of starting from I coming back to I in n steps, that n could be 1, 2, 3 and so on, which are strictly positive, and you collect all those n's which satisfies this. Remember, this is not Fii, this is Pii, right. So, this is Pii n, and you collect all those n's and you find the greatest common divisor of all those n's, right. Then that would be is what we call it as the period for a particular state. Now, if this period for the particular state I is 1, then we say that state is said to be aperiodic, and if this period of this is equal to some gamma which is strictly greater than 1, then the state I is said to be periodic with period gamma, right. Now, for example, consider this chain, right. So, this is essentially you have starting from say 0, 1, 2, -1, -2 and so on. So, what we are saying is that this probability is A, this probability is B, right, and this probability is C. Okay. Now, we are saying that A is strictly greater than 0, B is strictly greater than 0, C is greater than or equal to 0. Right. Of course, I have drawn this figure only for this one particular state, but of course, for every state this is true, right. So, you will have this behavior. This is the general description of such a chain, such a Markov chain, right. So, you will have all these self loops and everything, right. For a typical state only, typically one would represent, because that is sufficient to determine that part. Okay. Now, in this case, so this is what it is. So, now you see here like what is the period. Now, starting from 0, right, I can come back to 0 in one step provided my C is strictly greater than 0, right. Suppose, because this is C greater than or equal to 0. So, I am looking at different cases where C is equal to 0, C is greater than 0. Now, this link or this loop would exist provided C is strictly greater than 0. When C is equal to 0, this will not be existing, right, as you understand. So, only this left right movement would be there. In that case, for C strictly C equal to 0 case, you can reach 0. Starting from 0, you can come back to 0 in how many steps you will see? One step it is not possible, 2 step yes it is possible. You can go either to the right and the next step you can come back to this, or you can go to the left and next step you can come back. So, in either way, like there is a strictly positive probability that you will come back to that in 2 steps. Now, the same thing, C is equal to 0. So, whether in 3 step it is possible? No, because there is no self loop in any of these places. So, it has to go here, here. So, only in even number of steps you can reach back to a particular state starting from that particular state, right. So, your D of I would be equal to 1 or 2 provided if C is strictly greater than 0 and C equal to 0, right. So, that is what you will end up with in this particular case, the periodicity of this particular Markov chain, right. You see here the use of this state transition diagram, like one can easily analyze, like rather than looking at the numbers and so on, using these figures. So, that is why immediately it is useful to draw the transition diagram, so that accessibility, communication, how many classes are there, everything it is evident if you use this kind of periodic. Now, you see here that the previous example that we said we will look at it later, and you will see here what happens, right. This is the Markov chain in 4 states with this transition probabilities. Now, once I draw the figure 0, 1, 2, 3, right. Now, you can see here all these probabilities are all plugged into these values here. Now, you see here state 0 and 1 form one communicating class, right. 2 is one communicating class, 3 is another communicating class. So, in this has 3 classes, because from 3 I can come back only to 3, I cannot go back to 2 or 1 or 0. Done. So, this is a closed set, right. This is a closed set. Now, and it is a communicating class, it is a closed set. Now, you will have here 0 and 1 if I look at it. From 0 I can come back to 0, I can go to 1 and then come back to 0. So, 0 and 1 are communicating with each other. So, what you have here is that this 0 and 1 form one communicating class, and which is also a closed set, because there is no state outside of this, it can be reached from inside, right. So, this is, you cannot reach from 0 and 1 either 2 or 3. Same thing with 3, from 3 you cannot reach any of this 0, 1 or 2. So, 3 is also a closed set, 0 and 1 is also a closed set. Now, 2 basically what happens, like you can come back to 2, fine, but it is also a communicating class if you want to say, because it communicates with itself. But from 2 you can reach 0, you can reach 1 or you can reach 3. Now, from 2 once you reach 0, there is no way you can come back to 2, and from 1 2 if you reach 1, again there is no way you can come back to 2. The same thing, from 2 if you reach 3, there is no way you can come. So, this is not a closed set, this is a communicating. There are 4 states are there, 3 classes are there, 2 of them are closed sets and this is not closed, right. And since it has more than one communicating class, obviously this chain is reducible. Now, the reducibility part, suppose if you look at, this is one closed communicating class, this is one closed communicating class, right, this states form it. Now, if you look at the corresponding part in the stochastic TPM, you will see here, for example, for the first 2 states, this is what is the corresponding matrix, and now you see that this itself is a stochastic matrix, right, rho sum is equal to 1 and non-negative. Similarly, for the state 3, this is the corresponding transition probability matrix, right. So, this itself is a 1 by n matrix. So, this itself is a transition probability matrix, right. Whereas, for this state 2, you do not have that properties that you are seeing it here, right. So, this is open. So, in any Markov chain, whenever it is reducible, it will so happen that there is there will be n number of open communicating classes, and you will have that recurrent transition. So, these are all recurrent or positive recurrent states and so on. You can analyze this. So, with some more results in hand, one can do that thing. So, these are the some more results that we have with respect to this. These are all simply we are stating it, but intuitively also it should make sense. You can think a bit more probabilistically to understand that this is actually the case that will happen here. Say for example, if you are looking at the number of visits, okay, for any state I, suppose Ni be the number of visits to state I of the process. Number of visits means we are talking about the Markov chain. Then if the number of visit is infinity starting from I, the number of visits is infinity, right, the probability of that is equal to 1, then the state I is recurrent. That is the meaning of recurrence, that starting from I with probability 1, it will come back to itself at some point of time, right. Once it comes back, then again starting from that point, again it will come back to that. So, that means it will keep coming back, it will the state the process the state I will recur infinitely often. So, obviously the number of visits to this is infinity, right, and hence this probability would be equal to 1, and that would imply that I is recurrent, and here I is transient if implies that this number of visits to this state I would be following a geometric distribution with probability 1 minus Fii, right. Fii n means like this is basically you are coming back, this is Fii n means Fii is the probability of starting from my probability of ever returning to state I again. Okay. So, this random variable would then be geometric distributed, where Fii is given to be this, that is what it is. Okay. right. So, here for example, in the previous example if I look at it, so here, so this will be recurrent. So, suppose if it comes back to this in one step, again it can take this route, or it can go here and it can loop something and comes back here, anything it can happen. So, this 0 will be visited again and again and again infinite number of times, whereas in 2 suppose if you take for example, right, it can loop for some time, but at some point of time it will escape because the probability of going out from, whereas in 3 it will not happen, right, it will always loop 1, there is no chance that it can escape from, the process can escape from the state 3, but in this particular case the process can escape from state 2 because with probability 1 by 4 it can go here, with 1 by 4 it can go here, with 1 by 4 it can go here, and 1 by 4 only it will loop. So, how long it will loop? It is basically the question of the first time 2, there is no, it is not looping to itself, that is all. So, that is what it is essentially will turn out to be. So, the first time something happening in a experiment with binary outcome is basically geometric distributed. So, that is what you will get here. There is a corollary to this. What does that mean? Is that since this is happening, so PIIN, right, so this would be infinity. If state I is recurrent, PIIN, because there will be a positive value, positive value, not just, it will be some value which will be constant in some sense, right. So, that will be repeating again and again in this sum. So, the total sum would be equal to infinity, and transient if this will be finite. So, this is one can update as a corollary from this kind of thing. So, basically probability of xn equal to I for infinitely many n given xi is equal to I is equal to 1 if it is recurrent and 0 if it is transient. That is what these probabilities can be expressed in terms of this. Now, also you can see if the state space is finite, these are all important points which will be used throughout. So, you need to pay little attention to this. If the state space is finite, then at least one state must be recurrent. It cannot be that all the states can be transient, because if it escapes from all the states, then where will it go? It has to be at some state at any point of time, right. So, that means all the states cannot be transient and at least one state must be recurrent. Okay. Then another thing is this positive recurrence, null recurrence, transients, these are all class properties. It helps us a lot when we see this result. Also, all the states in a class have the same period. So, periodicity is also a class property, right. So, if I go back, if I look at here, the period is 1. If I compute it for one particular state 0, right, whether it is c greater than 0 or c is equal to 0, if I state, since here in all the states form a single communicating class, this is also true for all the states. Similarly, recurrence, if I find that one state is recurrent, then all the states will be recurrent. If one state is positive recurrent, all the states will be positive recurrent. If one state is transient, all the states will be transient. That is important, because then you do not need to look at differently. In this particular example, for example, from 0 and 1 class, so I can handle only one of them, that will do, because the same property holds for 1, so the state 1. Now, for state 2 I have to handle separately, for state 3 I have to handle separately, because from any of these I cannot infer anything from here, right. That is what it is. So, this is a class property, all these things, recurrence, positive recurrence, null recurrence, transient, periodicity, all of them are class property. So, if it happens with one state, it will happen with all the states in that particular communicating class. Now, all states of a finite Markov chain, if the chain is irreducible, they must be positive recurrent, because they are irreducible. So, they form a single communicating class, and we just state that okay, if it is finite, then at least one state must be recurrent. So, that means that at least one state is recurrent, single communicating class. So, all states are recurrent, right. So, finite, so that will also induce that all states are also positive recurrent. So, if I is recurrent and from I you can reach j, then Fji, right, which means starting from j reaching to I, if this time is finite, the probability of this is equal to 1 and j is recurrent. This is not true if I is transient. If I is recurrent, from I you can reach to j, then fji will also be equal to 1, which means that from starting from I you will also reach j in a finite amount of time is also 1, and hence j is also recurrent. So, I and j are recurrent together, and this is not true for if I is transient. And suppose if xn is irreducible and recurrent, then for all I in this particular quantity, which is the starting from initial distribution mu, probability that Ti is less than infinity if it is be equal to 1 for a chain which is irreducible and recurrent, right. Obviously, if it is irreducible, all states communicate with each other and it is a recurrent, it will come back to 1. So, no matter what is the initial distribution, this will happen. That is what it means. Here the thing is that the independent of this will happen. That is what it is. So, these are some of the properties of Markov chains that we are seeing in this lecture. We will see few more properties, which is what will complete our discussion of Markov chain, and that is what will be used. So, to develop, to use, to come to that kind of conclusions, like we need all these notions: accessibility, communication, irreducibility, closedness, or periodicity, recurrence, positive recurrence, null recurrent, transient, because this is all is what. So, how one can determine what do they mean actually in a Markov chain scenario. So, all these things is what we have seen. So, we will continue in the next lecture with some more properties. Okay. Thank you. Bye.